So some isomers of C5H12 is one with the larger surface area. It's going to have greater London dispersion forces, and so we see the neopentane has less dispersion force and hence a lower boiling point. So the more electrons something has, so we have some molecules and some atoms. And if we look at krypton up there, weighs almost 84, 36 electrons. So it has a higher boiling point than krypton, which is higher than argon. And remember that first slide we saw chlorine as a gas, bromine as a liquid, and iodine as a solid. Larger electrons have larger electron clouds, easier to polarize, so greater London dispersion forces holding that together in the condensed phase. So hydrogen bonding, what is that? Well, you might have learned in the gas chapter that you need a highly polar atom, small one, like fluorine, oxygen, or nitrogen, and hydrogen bonded to that. So a special type of intermolecular force between a hydrogen atom in a polar bond and a non-bonding electron pair on a small nearby electronegative atom, ion or ion, and these are the only atoms you got to look out for: fluorine, oxygen, and nitrogen. So over here, these red dots depict a force acting between these two water molecules. Here's a force acting between two molecules of hydrogen chloride. Here's a force acting between two molecules of ammonia. But now we see ammonia and water hydrogen bonding, and that is what hydrogen bonding is. So an interesting thing with hydrogen bonding is here we have ice, and these water molecules are locked into place. We have solid water, and nature being what it is makes these holes, and that makes ice less dense than water, so it floats. So here we see a bunch of elements in column 6. We have oxygen, then we're going to have sulfur, then we're going to have selenium, and then finally below that, tellurium. And we see this nice trend of things increasing here. These all go up, CH4 doesn't. So what is going on? Well, these are the species that can hydrogen bond. So this line here follows our general trend, the nonpolar series of SN4 down to CH4. Follow the expected trend for London dispersion forces. The London dispersion forces are increasing as we go this way, and the smallest molecule has the lowest boiling point, the weakest intermolecular forces. These here are kind of off the map. Water is particularly off the map because it weighs 18 grams per mole roughly. CH4 weighs 16 grams per mole roughly. If it wasn't for hydrogen bonding, water would be, down here, kind of following the general trend. So hydrogen bonding, we say, is a strong intermolecular force. It's one of the stronger ones. So this is a foreshadowing for great things to come in chapter 13. This would be a fourth intermolecular force, which is an ion interacting with a dipole. The first three would be London dispersion, dipole-dipole, and hydrogen bonding. So this is something that typically only happens in solution, important to the solution process. The strength of these forces is what makes it possible for ionic substances to dissolve in polar salt. So oxygen, more electronegative than hydrogen. So water has a net dipole. You can think of a partial positive charge on the hydrogens. And so here you see the hydrogen ends of water orientating themselves towards the negatively charged chlorine. All right, out here on oxygen we have a negative charge, and those orientate themselves, counterbalance that positive charge on sodium. So a lot of quiz questions might say, which of the following species can hydrogen bond? Or which of the following is an example of London dispersion? So this little flow chart can perhaps help us. First thing we ask, are ions present? So let's just say we have CH4. CH4, no ions present. Are polar molecules present? Well, CH4 isn't a polar molecule. No. So we have dispersion forces only. And then all of our diatomic elements, N2, Br2, would come down this way. Let's do methanol. Are ions present? No. Are polar molecules present? Yes. Are hydrogen atoms bonded to nitrogen, oxygen, or fluorine? With methanol, that would be a yes. So we have hydrogen bonding. And then finally, some molecules with dipoles. Are ions present? No. Are polar molecules present? Yes. Do we have a hydrogen bonded to a nitrogen, oxygen, or fluorine? No. So that's just going to be dipole only. And then the last thing we just looked at, like sodium chloride dissolved up in water. Are ions present? Yes. Are polar molecules involved? Yes. So now we have ion-dipole forces. Are ions present? Are polar molecules present? So here we're looking at a crystal of salt that's ionically bonded together. And the inner attraction here would be lattice energy, holding these solids together. So here's two molecules that have the same weight, acetic acid, and one propanol. And we see hydrogen bonding can occur. Here we have two places. Each molecule can form two hydrogen bonds with a neighboring molecule. And so it has a boiling point, 391 Kelvin, which is 21 degrees higher than propanol's boiling point, which can only hydrogen bond in one position. So it's this attraction. These intermolecular forces are going to dictate physical properties like melting point, boiling point. So your grandma might have said, "You're moving like molasses in January." What does that mean? Well, it's slow, yeah. So things like honey, molasses. I like my molasses on grits. If you're into hot cereal. Grits and cornbread. I don't think I like molasses on anything else. It's kind of has a bitter taste to it a little bit. So viscosity is a resistance to flow. And so if molecules are attracted to each other, it kind of slows them down when they move past each other. Viscosity increases with stronger intermolecular forces and decreases with higher temperatures. So molasses, I think of, it's kind of like syrup, big chains of carbohydrates. Here we just got big chains of hydrocarbons. But nevertheless, as we get longer and longer chains, viscosity goes up. And it says viscosity decreases with higher temperature. So you want your molasses to flow easy, you put it in the microwave. Or you put that honey bear in the microwave. You deform all the plastic. You realize you're going to die of cancer early from all the plastic you're eating when you microwave the honey bear.
You can get plastic from a lot of other places too, though.
Oh yeah. Get yourself a still water bottle. I'm told every plastic bottle of drinking water has microscopic pieces of plastic. So intermolecular forces gives rise to this thing called surface tension. Maybe you've seen these down around the Platte and the slower pools up by the bank. And so a water molecule out here in the middle feels attracted to every molecule around it, so it's kind of like free. But up here on the surface, this molecule here, I might as well use their drawing, It's being pulled that way, and down. And you think about it, it kind of makes it like a drum head. That's what I think of as a drum head being pulled tight. It gives rise to surface tension. Surface tension results from the net inward force experienced by the molecules on the surface of a liquid. And it's also going to make a small piece of water beat up, form a sphere. So if we have an intermolecular force that bind similar molecules to one another, we call it a cohesive force. An intermolecular force that bind a substance to a surface are called adhesive forces. So here we see mercury, and this must be water. So glass is this silicon dioxide, and so for whatever reason, water and glass have a attraction for each other called adhesive, and it's greater than cohesive. So we see a meniscus like this, and this is due to that surface tension phenomenon that we just saw earlier. It's being attracted to the sides, and the molecules on the surface are being pulled down by being attracted to the other molecules right below the surface, and it stretches this thing and has this shape. So over here, mercury would rather be attracted to itself than the glass. So here the cohesive forces are larger than the adhesive, and we have a meniscus that forms this way. So the barometer I read in class, I read from the top of the meniscus. In your graduated cylinder, you read the bottom of the meniscus. So when a liquid goes to a gas, we call that vaporization. When you have a icy drink on a humid day, beads form on the outside, we call that condensation. Of course, when a liquid turns into a solid, we call that freezing. Going the other way, we might call it melting. And you look this up in the thermodynamic appendix. You look up a heat of fusion for water, and you look up a heat of vaporization for water. So fusion and freezing are synonyms. Now here is a good place to end, evidently. I don't get to my fancy example. Deposition and sublimation. I'll ask you all the questions on that.